Alright, so in the last video we saw that the neural gas, why it's called neural gas, is that the idea is that every data point in your set is given an attracting force on the centers. And so the centers, every time you pick a data point, you move the centers towards that data point. And so what's happening then is that, in a circle might be a problem, right? Because if you have competing forces like that, the middle is going to be in a kind of a hole there. But usually you're not right directly in the middle. So the idea is that maybe the centers are out here somewhere, and hopefully what happens is that the centers are attracted to the data set and then embed themselves into the data set. Okay, so that's why the neural gas might be chosen over other algorithms. There's another reason why it might be chosen, and that's a little bit harder to understand maybe, and that is that we would like the clustering to be topology preserving. Whatever that means. So that's what we're going to talk about. What is topology preserving? Well, the idea is that the cluster's centers are going to have, we're going to put links between the cluster centers. Whoops. We're going to link them up. So it looks like you could think of this as a tree, right? And the idea is that to go from like one center to the other, you have to move along the edges to get there. And so what we're hoping is that if I have data, in one cluster like this and in another cluster like this, I'd like my algorithm to tell me that I can't go from this set to this set. Okay, so somehow, there would be no connections here, right? And so this is the hope of building a diagram like this. Okay, so what's the problem? Well, you run into a couple of issues when you do that. Suppose that you have cluster centers that you start off with, with that kind of a topology. So this is what we mean by a topology, is kind of the metric is the link. We're going to use the link distances for the metric. That's what I'm trying to say. Suppose I'm trying to map this to the plane. So this is my data in the plane. Well, what's going to end up happening is that your line is going to end up getting, I think I just drew more points than I had before. The problem here is that points that were far away, or should be far away, so for example these 2 points, are close together. So points that are far away are getting mapped together in the plane. So that could be a problem. Similarly, points that are close together here, so I think that's going to work. So this is like a one-directional. So if these two are together, they're still together here, and if these are together, they're still together there, and so on. So it's only really one direction that's the problem. But we want to be able to go both directions. So suppose that I've got a three-dimensional cube, right? And this is for my cluster centers. Oops, I'm thinking of my cluster centers as being in 3D now, and I move my clusters to the plane. So somehow I'm doing this projection. Right. Well, what's going to happen is that this cube is going to get squashed, right? And do you see what the issue is going to be? Again, we want points that are close together being plotted close together here, and vice versa. Points that are close together over in the data graph should be close together in the cube. And so we're going to there's going to be a dimensional mismatch here, and so we're going to run into trouble. And so what's the best kind of linkage topology that we might have between our clusters if we have a planar set? Well, that would be, well, let me just go ahead and draw the cluster centers in here. That would be a grid, right? A two-dimensional grid. And so this would be what we call a topology preserving map, or preserving clustering. And this is not topology preserving. And this is not topology preserving. Okay. So how are we going to construct such a linkage for the neural gas? Well, what we're going to do is, given some data and given some centers, suppose I happen to select this data point X. Then I didn't draw it very well, but this center may be closer than this one, but this one is definitely the second closest center. And so what I'm going to be doing is I'm going to be drawing a line between the winning center and the next winning center. Okay. By the way, remember these are being attracted to the point X as well, right? And you're going to do that for every X. So if this is my X, then this would be the winner, and this would be is that second closest? I'm just kind of eyeballing it there. Let me put it closer to here. There we go. So this would be closest and this would be second closest, right? And so then I would draw a line segment in between those, if this is my X. Okay. The problem is that sometimes I might be putting in an edge and then the centers move away from each other, and so I may not want to keep the edge, and so we're going to draw, I should be writing this down. Draw an edge between closest and next closest center. Keep track of how long it's been since the edge was drawn, and edges, if the edge time is greater than some value, let me check real quick. I'm using capital T in the notes. Then remove the edge. Okay, and so the edges are going to be kept in a matrix, right? So the matrix in the code that you'll read, M is going to be the connection matrix. So Mij is equal to 1 if center I and J are connected, 0 otherwise. And I would mention that this is symmetric. So that is, if center I is connected to center J is connected to center I. And then we will also keep a matrix Tij. And so that's going to be the time since edge Ij was created. I guess I didn't really need a thing for that. Good. All right. And so in the algorithm, you're going to see things being updated. So let's go ahead and write down the algorithm, the neural gas algorithm. One, select X at random, and that should be uniformly random. Find the k closest points, k closest centers. Maybe I should put that on a different line, huh? find the k closest centers. And then the centers are updated. Update the closest centers. Using our update rule, that was CIK equals CIK plus epsilon times the exponential function minus SIK divided by lambda times x minus CIK. These are vectors, by the way, right? Good. And then we update the connection and time matrix. This will be between I1 and I2, right? And then we remove old connections. And then we repeat. I should say, at some point we're going to have to update our parameters. What parameters? Remember, some of these values are going to 0, right? Epsilon needs to be updated, lambda needs to be updated, and time needs to be updated. Because our time values are going to change according to the iteration as well. Okay, and then 7 is repeat. Good. And then the stopping criterion we'll have to figure out. We're out of time right now, but what I want to talk about in the next video is just how to do this parameter update, because it's a popular update for a lot of different algorithms. And then let's see, I'm going to have to switch gears because I want to give you an example, and I'll have to do that on the computer, on a different computer. All right, so see you in the next video.